Hello everyone. Today we are diving into one of the most legendary and persistent vulnerabilities in the history of cybersecurity, the buffer overflow. If you've ever wondered how a simple programming error can allow a hacker to take over a global network or spy on a smartphone, you're in the right place. To understand a buffer overflow, imagine you have an 8-ounce glass and you try to pour 12 ounces of milk into it. What happens? The milk doesn't just vanish, it spills over the counter, soaking everything nearby. In the world of computers, that spillover is exactly what causes a buffer overflow, and the nearby items being soaked are critical parts of the computer's memory. To get technical, computers use temporary storage areas called buffers to hold data while it's being moved from one place to another. Most programs manage this data in an area called the stack. In a healthy program, the stack stores data like your username or password, followed by something called a return address. This address is like a GPS coordinate that tells the computer where to go next after it finishes its current task. When an attacker performs a buffer overflow, they send much more data than the buffer can handle. This overflow travels down the stack and overwrites that return address. Instead of the program continuing normally, the attacker points the return address to their own malicious code, known as shellcode. Suddenly, the computer isn't following the original program anymore. It's doing exactly what the hacker wants. This isn't just a theoretical problem. Buffer overflows have caused some of the most expensive and famous digital disasters in history. Back in 1988, the Morris worm exploited a buffer overflow to shut down 10% of the entire internet in just hours. In 2003, the SQL Slammer worm used the same trick to crash ATMs and slow global internet traffic to a crawl. Even modern apps aren't immune. In 2019, a buffer overflow vulnerability was discovered in WhatsApp. Attackers could install spyware on a target's phone just by making a voice call. The victim didn't even have to pick up. This shows that even with our advanced technology, these old-school bugs are still a massive threat. So how do we stop this? Developers and security engineers have built several layers of defense. First, we use bounds checking. Modern programming languages like Python or Java do this automatically, but in languages like C or C++, programmers must manually ensure that the input fits the buffer. Second, we use ASLR, or address space layout randomization. This shuffles the memory locations every time a program runs, making it nearly impossible for a hacker to predict where to point that return address. Finally, we use stack canaries. Just like miners use canaries to detect toxic gas, developers place a small, secret value next to the return address. If a buffer overflows, it kills the canary first. The system detects this change and shuts the program down before the hacker's code can ever run. Buffer overflows are a classic example of why secure coding is so vital. By understanding these fundamentals, we can build a safer digital world. If you found this breakdown helpful, let me know. Would you like me to walk you through a step-by-step lab simulation of how these vulnerabilities are discovered using a debugger?